So welcome back to the fourth semester last module, aliphatic hydrocarbons. The word itself indicates that aliphatic hydrocarbons, there is no cyclic aromatic ring structure involved in this module. It is all about aliphatic and then hydrocarbons. Hydrogen and carbons are the major um, um, elements present in this kind of compounds. Next, let us have introduction. You will be knowing all these things, but just to refresh your mind, hydrocarbons are compounds containing only carbon and hydrogen, and several of them are used as fuels. As you know, hydrocarbons can be used as fuels like kerosene, petrol, diesel, all these are all mixtures of hydrocarbons, and depending on the number of carbon atoms, these are classified. And the major source of aliphatic hydrocarbon is petroleum, which upon fractional distillation yields petrol, diesel, kerosene, etc. Okay, and these fuels are a mixture of aliphatic hydrocarbons and are rich source of energy. Okay, so we are using a mixture of hydrocarbons in the form of petrol, diesel, kerosene, etc. in order to for our daily applications like cooking and also used in vehicles, etc. Okay, so these are rich source of energy. The major component of natural gas found in the upper strata during the drilling of oil wells is methane. Okay, so methane is a gas, as you know. Methane we are normally obtained from the upper portion of the the oil wells. Okay, and it will be trapped over there and can be taken out from the upper part of the oil wells. The major content of CNG is compressed natural gas, is methane, and it is used as a fuel of automobiles. CNG is compressed natural gas, is major content, or it is only it contains only methane gas. Next is LNG, liquefied natural gas, also a fuel, and is obtained by liquefaction of the mixture of propane and butane. Propane is used more in winter and butane used more in summer. It is mainly because propane, it's LPG, is normally is a mixture of propane and butane, but in the Europe, US, and particularly in the winter time, the propane content will be more than butane. So this is mainly because during high cold climate, propane can produce enough vapors for the ignition purpose. Okay, and aliphatic hydrocarbons are also used for the manufacture of polymers like polythene, polypropylene, etc. Okay, so for the preparation of polythene, we are getting ethene or ethylene from the petroleum industry. For the making of polypropylene, we are getting propylene or propene from the petroleum industry. Higher hydrocarbons used as solvents and as the starting material for manufacture of many dyes and drugs. Okay, so these petroleum products or the hydrocarbons obtained from them have variety of uses in different fields. Okay, all right. And now we are coming to alkanes, and you will be knowing all about the introduction of alkanes. Just to refresh your minds, we will just have to discuss the points written here. The saturated aliphatic hydrocarbons are called alkanes. So these are saturated, does not contain any carbon-carbon double bond, any other functional groups, and they form a homologous series having a general formula CnH2n plus 2. So you will be knowing all these things. And on account of saturated nature, alkanes are relatively inert. Since it doesn't contain any carbon-carbon double bond or any other functional group, these are relatively inert in nature and stable to the common reagents such as oxidants, reductants, acids, bases, etc. Okay, so they have very limited reactivity towards other chemicals. They are also called paraffins. The name paraffin comes from the Latin word param means little, affinis means affinity, little affinity towards other chemicals. So it is called paraffins. The main source of alkanes is natural gas and petroleum. Okay, and natural gas was found near petroleum wells, contains a number of solid alkanes. Okay, and then methane is the principal constituent of marsh gas produced by the anaerobic fermentation of cellulose. Okay, So marsh places, as you know, ചതുപ്പുനിലം എന്ന് പറയുന്ന സ്ഥലത്ത്, അതായത് for example like people, you might have heard about some people are dying when they enter to the wells for cleaning it, because that kind of wells were not actually cleaning for a long time, so it should definitely contains methane and carbon monoxide gas. Okay, so marshy places or the bottom of the well may contain the kind of muds, and lot of bacteria will also make carbon monoxide and methane over there. Okay, some plant waxes and bees waxes contain some solid alkali. Okay, so that's an introduction, and now we are coming to the IUPAC nomenclature of alkanes. You will be knowing all this also. IUPAC nomenclature of alkanes is nothing but first you have to find out which is the longest hydrocarbon chain, and that is the parent hydrocarbon, and we need to give numbering system in order to identify the substituent group present on the parent hydrocarbon chain. Okay, so for example, if there is a substituent group on the parent hydrocarbon chain, and the substituent group should get the least number, so we have to write the number in such a way that the substituent group should get the least number. Okay, and then if in certain cases the same substituent if comes on different carbon atoms twice or thrice, if it comes twice we normally give the name by giving di. If three substituent groups are there, we normally give tri. And if two different substituent groups are there, so we have to go for the alphabetic order. Which comes first in the alphabetic order should be named first. Okay, but this is all essence of these points. So just let us have a look at the points written here. Select the longest continuous carbon chain, or it is called parent structure, and then consider the compound to have been derived from this structure by the replacement of hydrogen by various alkyl groups. Okay, the parent carbon chain is numbered in if necessary, and in numbering start at whichever end result in the use of lowest number. Don't bother about what is written here, you just bother about what I have explained just now. If the name alkyl group occurs more than once as a side chain, use the prefix di, tri, tetra, etc. So you will come to know all this when we discuss the examples in the next two slides. If there are several different alkyl groups attached to the parent chain, name them in alphabetic order. Okay, and if the two substituents are found in equivalent positions, so we have to give the number 2 times. In naming branched alkyl groups, use iso related to type of structure you have to identify and then name it. Okay, so let us discuss some examples. In this case, it is what is called, this compound is called butane because it contains 1, 2, 3, 4 carbon atoms. 4 means buta, and final name ANE. Okay, because it is alkane, so last 3 words is ANE. So butane. Okay, and in this case there is a substituent, so you have to find out the parent longest hydrocarbon present in this compound. So 1, 2, 3, or you can write as 1, 2, 3. Okay, in both cases it is the same. Okay, so the second carbon atom there is a substituent. Okay, so this is propa, 3 are there, so this is the propane. Parent hydrocarbon chain is propane, second carbon atom C3, so this compound is 2-methyl propane. Okay, and when you look at this compound 1, 2, 3, 4, 5, there is no substituent groups. 5 is penta, we call it as pentane. Okay, and in this one 1, 2, 3 carbon atoms are there. It is parent hydrocarbon chain is propane, and 2 substituents are there on the second carbon atom, so this is called 2 identical groups are attached to it, so this is methyl group. So this compound is called 2 methyl groups are there, 2 dimethyl propane. Okay, and if you look at this one, here we have CH3 group on the second carbon atom, so we have to start number in such a way that the substituent group should get the least number. So you can start the numbering from here 1, 2. So if you start the numbering from here 1, 2, 3, 4, so that is not the right way. So we have to start numbering from here 1, 2, 3, 4, 5. So this is pentane, and then second position a methyl group is there. So this compound is 2-methyl pentane. And look at this compound, second 1 2. So we have to start numbering from here, because then only it will get, this substituent will get the least number. 1 2 3 4 5, 2 methyl groups are there, so we can call this compound as 2 methyl 2 3 methyl dimethyl pentane. Okay, and look at here, two different substituent groups are there. One is methyl and second is ethyl. Okay, so we have to look at which substituent group comes first in the alphabetic order. Ethyl comes first, so we have to first mention this one. So 1 2 3 4 5. Okay, so here so 2 3 ethyl, 2 methyl pentane. Okay, all right. So when you look at the next example, so we have to start numbering from here. 1 2, second carbon atom, 2 methyl groups are there. Fourth carbon atom, an ethyl group is there, so we have to first mention the ethyl. Okay, so this is 4 ethyl 2 2 dimethyl, 2 2 dimethyl heptane. 1 2 3 4 5 6 7, 7 means heptane. Okay, and when we look at this one, here we have 1 2 3 4 5 6 7 8. Okay, 8 carbon atoms are there, so that is octa. So the pyrene hydrocarbon is octane. So we have to start numbering from here. 1 2 3 4 5. So all the substituents on the pyrene hydrocarbon chains are methyl groups only. So its positions on the third position, 3 4 5 6, 6 trimethyl octane. Okay, and now we are look at the little more complicated structure like this. Here we have to start numbering from here. The third carbon atom, 2 ethyl groups are there, and then fourth carbon atom, 1 methyl group is there, and fifth carbon atom there is an isopropyl group is there. Okay, so 3 different groups are attached as the substituents. So in the alphabetic order, first we have to give the ethyl. So this compound is 3 3 diethyl. Okay, and then methyl and isopropyl. So isopropyl comes first in the alphabetic order, so this is 5 isopropyl for methyl octane. Okay, next let us discuss the structural isomerism in alkane. Alkanes show structural isomerism. Structural isomerism means hydrocarbon chain structure varies with the same molecular formula. Okay, so here we have a compound of molecular formula C4H10. So we have to have 4 carbon atoms in the structure and 10 hydrogen atoms also present in the structure. So we can write it as 4 carbon atoms initially we write, and then give the hydrogen atoms. So the normal butane, and its structure is different. Okay, 2 methyl propane. Okay, and if we take another example, C2H12. Okay, so in this case we get 3 structures with the same molecular formula. Okay, so 3 structural isomers are possible for this particular compound. So one is pentane, 5 carbon atoms are attached and 12 hydrogen atoms are there, 3 5 7 9 12. Okay, and then 3 methyl butane, and another one is 2 2 dimethyl propane. So all these possibilities you have to look at, and then only you have to write the structures. Now let us discuss the preparation of alkanes. First method is from alkyl halide. Okay, so from alkyl halide we can make alkanes. First method is a reduction of alkyl halides. So here we can use the reducing agents like zinc HCl or zinc in acetic acid or zinc copper couple in ethanol, or magnesium mercury water gives alkanes in good yield. Okay, so all these are prepared from alkyl halides. So alkyl halide reacting with zinc in HCl, the reduction is taking place. Reduction means addition of hydrogen, and then we get alkane. Okay, and if we take ethyl iodide as an example, reduction is taking place with the zinc in HCl, and then we get ethene. Okay, so just replace the iodine and hydrogen is added to it. Reduction has taken place. There is an indirect reduction of an alkyl halide to alkene is possible by treating it first with the magnesium in either solution to get Grignard reagent. We have already discussed it in the last, we have already discussed this point in the 5th sem, and then decomposing this with water or reacting it with active hydrogen compound. So we take initial starting compound is alkyl halide reacting with the magnesium in dry ether, then we get a Grignard reagent RMGX, which is reacting with the water, then we get alkane. Okay. For example, we take a methyl iodide CH3I magnesium in dry ether, then we get methyl magnesium iodide reacting with the water, we get methane and magnesium hydroxyiodide. Okay. And if we take ethyl iodide reacting with the magnesium, ethyl magnesium iodide reacting with the water, then we get ethane. Okay. All right. So next method is Wood's reaction. Alkyl halides, when treated with, so our starting material is alkyl halide, and it reacts with metallic sodium in dry ether. It gives higher alkanes. So in this method, previous method, it was not giving the higher alkanes, or there is no addition of any carbon atom along with the alkyl halide. Okay, but in this case, there should be a step-up reaction, or more number of carbon atoms will be possible on the product. Okay, higher alkanes can be prepared by this method using alkyl halide and sodium metal in dry ether. So here we have taken alkyl halide RX reacting with metallic sodium 2Na plus RX alkyl halide, and in the dry ether we get alkene. So 2 carbon atoms are there instead of 1 carbon atom present in the alkyl halide. Okay. And then if you take a specific example of methyl bromide CH3Br reacting with sodium metal CH3Br methyl bromide dry ether, we get ethane. Okay. And then if you take ethyl bromide CH3CH2Br reacting with sodium metal, here we get CH3CH2Br, again one more dry ether, then we get butane CH3CH2 CH2CH3. Okay. So it's a step up reaction. And if we take two different alkyl halides, here we have 2 carbon atoms, here we have only 1 carbon atom. So in that case, that's a very particular case. In that case, we normally end up with a mixture of products in the reaction system. So that is not advisable, because you have to remove all these things and we may not get desired product in high yield. Okay, so let us take an example. Ethyl bromide reacting with the methyl bromide in the presence of sodium. Okay, so here first this reaction will take place, dry ether, we get propane, and in the second case this compound itself, methyl bromide itself, will react with the sodium metal, and then we get ethane. And in the third case, ethyl bromide itself will react with the metallic sodium in dry ether, we get butane, a mixture of compounds propane, ethane, butane. Okay, so this is the limitations of Wood's reaction, because we can normally do the reaction with similar alkyl halide. Otherwise, we will always end up with a mixture of compounds. So what are the limitations of Wood's reaction, Wood's method? The reaction fails with the tertiary alkyl halides. Normally, this reaction we do with the primary alkyl halide, not with the tertiary alkyl halide. And the halogen compounds with other reactive functional groups like OH, COH cannot be used. So if we have a COH group or any other functional group, we cannot do this reaction. So this is purely of alkyl halide reaction with metallic sodium. Although a convenient method for the preparation of symmetrical alkanes, it can be used for the preparation of symmetrical alkanes, it is not a good method for the preparation of unsymmetrical alkanes. That means this kind of reaction, mixed reaction, is not advisable in Wood's reaction. Okay, so this is a symmetrical alkene. Okay, because when you divide here, 2 equal halves are obtained, but here you cannot divide. Okay, so in this case you can divide, 2 equal halves will be obtained. That is what is called the symmetrical alkene. Okay, so this method is advisable for making symmetrical alkanes. Methane cannot be prepared by this method. So these are all the limitations of the Wood's method. Next is Corey-House reaction. When a suitable lithium dialkyl cuprate, so this is the reagent, lithium dialkyl cuprate is treated with a suitable alkyl halide in dry ether or dry tetrahydrofuran, excellent yield of the desired alkene can be obtained. This reaction is known as Corey-House